You know that feeling. You're trying to get a beautiful shot at night, maybe a cool cityscape or the stars, and what you end up with is just a noisy, grainy mess. Yeah, we've all been there. Well, today we are diving into some really fascinating research that's trying to fix that exact problem by, get this, teaching an AI how to see in extreme darkness. Let's dig into how it works. So, to really get why this happens, you got to think about what light actually is. When you snap a picture in almost total darkness, you're basically asking your camera's sensor to pull off a miracle. It's trying to piece together a detailed image from just a tiny handful of light particles, called photons. The result? It's almost always an image that's just full of digital noise and these blurry, undefined shapes. It's a fundamental challenge for any photographer.
So in this explainer, we're going to follow the whole story. We'll kick things off with the basic challenges seeing in the dark, and then this over-smoothing problem that totally stumped the early AI attempts. Then, we'll introduce the solution, DarkDiff, break down its key innovations, and finally look at the results, which are, well, pretty clear.
All right, let's start at square one, the actual physics behind the problem. You know, taking a great photo is all about capturing light. So, what happens when there's practically none to capture in the first place? This right here is the heart of the issue. A camera sensor, it basically works by counting photons. When there's plenty of light, it gets a ton of information to build a nice, clean, sharp image. But in the dark, that photon count plummets. The sensor gets a really weak, noisy signal, and that's the raw material that becomes that grainy photo you always end up deleting.
Now, every single digital camera has this thing inside called an image signal processor, or an ISP. Just think of it like a little photo editor that lives inside your camera. Its whole job is to take that noisy, raw data from the sensor and clean it up into the final picture you see. It does denoising, color correction, you name it. But when the data is super noisy, the ISP just gets overwhelmed. It ends up blurring details to try and hide the noise, and that creates what photographers call these oil painting artifacts. Not great.
So naturally, researchers were like, hey, let's throw some AI at this. But that first wave of AI enhancers, they ran smack into a huge roadblock. They kind of solved one problem, but they created a whole new one that was just as frustrating.
These early AI solutions pretty much went down two different paths. On one side, you had what are called regression-based models. Their goal was pure mathematical perfection. They wanted to minimize the error for every single pixel. The downside? They made these overly smooth, kind of blurry images. On the other side, you had these early generative models, called diffusion models, that tried to invent details to fill in the gaps. But they often hallucinated details that weren't there, and just got the colors all wrong. This quote here, it points to a core statistical problem called regression toward the mean. Basically, to minimize its chances of being wrong, the AI would just average out all the possibilities for a single pixel. It's a safe bet, sure, but it's also why you lose all those sharp, specific details, like the texture on a brick wall or the pattern on some fabric. It just plays it safe and ends up creating mush. So, the failure of these older methods really paved the way for something new. And this brings us to a brilliantly clever new strategy called DarkDiff. See, instead of trying to build a low-light expert from scratch, its creators decided to teach an existing master a brand new trick.
Okay, this is the key innovation. DarkDiff doesn't start from zero. It takes Stable Diffusion, which is a massive, incredibly powerful AI that's already been trained on billions of images from the internet, and it adapts it for this one very specific job, enhancing raw photos. You know, those unprocessed, data-rich files that come straight from the camera sensor? This is a total game changer, because it's leveraging an AI that already has this vast, built-in understanding of what the world is supposed to look like.
This whole process is called retasking. And here's the best analogy for it. Imagine you have a master painter who has spent their entire life studying every subject you can think of. Portraits, landscapes, everything. Retasking is like taking that master painter and teaching them the very specialized skill of restoring old, faded photographs. They already have all the foundational knowledge of light and texture and form. They just need to learn how to apply it to this new, specific problem. Okay, but how exactly do you teach a master painter this new skill? Well, DarkDiff introduces three specific technical innovations that make this retasking thing work so well. Let's take a look at the secret sauce.
So DarkDiff's architecture really stands on three main pillars. First up, there's a technique called region-based cross-attention. Second, a content-preserving autoencoder. And third, a final quality check using something called a decoder-based reconstruction loss. Don't worry, we'll break it down.
First up is region-based cross-attention. You see, a standard AI tries to look at the entire noisy image all at once, and that makes it lose the fine details. It's kind of like an artist staring at a whole photo instead of focusing on one little section at a time. DarkDiff's solution is brilliant. It breaks the image into smaller patches, forcing the AI to focus locally. This preserves all those nice textures and stops it from just making stuff up.
Next, we have the content-preserving VAE. To process an image, an AI often has to compress it, which risks losing really important details like faces or text. So what DarkDiff does is it adds these things called residual connections. Think of them like little informational shortcuts that let the fine details bypass the compression step. This makes sure that the original content, what makes the image what it is preserved. And finally, there's the decoder loss. So the AI does its work in this abstract, latent space. It's a compressed, mathematical version of the image, and sometimes that can cause the colors to shift. This final step is basically a quality control check back in the world of pixels. It penalizes any color mistakes to make absolutely sure the final photo looks right to the human eye.
So we've got the theory, we've got the architecture, but does it actually work? Let's get to the results and see how DarkDiff really stacks up against the competition.
Okay, before we check out the chart, you need to understand this key metric, LPIPS. Unlike older ways of measuring that just compare pixel values, LPIPS is designed to measure how similar two images look to an actual person. For a creative task like this one, it's the metric that really matters. And just remember, with LPIPS, a lower score is better.
And this chart? Well, this is where the data tells a pretty compelling story. You can see the competing methods are all scoring around 0.23, 0.24, and then there's DarkDiff, way down at 0.186. That is not just a small improvement, that is a massive leap forward in quality that you can actually see.
And that LPIS score translates directly to real-world results. This quote from the paper explains it perfectly. Where other state-of-the-art models blur out the textures of bushes and buildings into a smooth mess, DarkDiff is able to realistically reconstruct those fine details. It actually overcomes that core over-smoothing problem we talked about.
Look, this isn't just a tiny step forward. It's the next clear step in this whole evolutionary chain. We went from the traditional camera processors that just struggled with noise, to the regression AIs that over-smoothed everything, to those early generative models that just made stuff up. DarkDiff, with its whole retasking approach, really represents a new, much more effective way of doing things.
And this, right here, is the big takeaway. The success of DarkDiff isn't just about getting better night photos. It highlights a really powerful and efficient strategy in AI development. Sometimes, the best way to solve a new, niche problem isn't to start from scratch, but to find a powerful, generalist AI and just teach it a new, specialized skill.
It really makes you wonder, doesn't it? This technology is basically giving a camera a form of superhuman vision. So if we've successfully taught an AI to see in the dark, what's next? I mean, could we teach an AI to hear whispers from across a room, or to enhance our other senses in ways we can't even imagine yet?